Thanks. So most of the people who know me call me Adi. I lead the Scalable Systems team at Yahoo Research, which is actually now part of a much bigger company called Verizon Media. I'll say a couple of words about that in a moment. So this project is actually our first attempt to contribute to Druid as its internals developers. So I guess this talk will provide a different perspective and complement Itai's talk on the other side nicely. So the focus of this presentation actually is how we make the ingestion process into Druid faster and more efficient with the new scalable incremented index that we've developed at Yahoo. But let's start with first things first. So just a few words about us. So you probably how many of you heard the brand Verizon Media before coming to this talk? Nice. I actually expected less. So the Verizon Media is kind of Yahoo plus AOL combined together. Actually, we became part of Verizon post-acquisition about 2.5 years ago, and the company actually has businesses in both content advertising and platform technology. So I bet many of you have either used or at least heard of about very popular products like Yahoo Mail, Yahoo News, Finance, Sports, etc., and also a bunch of other products. Overall, we reach slightly less than 1 billion consumers worldwide. On the economy of scale side, it makes a lot of sense to us to run most of our systems internally on a private cloud. So this private cloud is running a huge variety of workloads, and it's built around a host of open source technologies like the whole Hadoop stack, Spark, and Druid for real-time analytics. So our team comes as part of a bigger organization that's called Yahoo Research. Historically we work in multiple areas that actually address the toughest problem that the product teams address. My own team works on the systems and infrastructure and how we can improve it through innovative algorithms and implemented in software. So physically we reside as part of the Yahoo Research Lab in Haifa, and as I said before, we want to make the systems that we work on fast, scalable, and reliable. We ended up having committers and on multiple open source projects like Apache, HBase, Apache, Phoenix, RocksDB. We are also proud contributors to data sketches, as Itai has described. This is the project that originally came out from Yahoo, and most recently Druid. This project is actually the first experimental feature that we would like to contribute. Okay. So just a couple of words about how we use Druid at Verizon Media Group. So since we are engaged in multiple products and multiple businesses, we use Druid all over the place for various analytics tasks, be it content analytics for accounting for the traffic to our websites and mobile applications, ad analytics, figuring out what's going on in our campaigns in the real time, deep user analytics, network and system monitoring, etc., etc. We host multiple petabytes of data. Unfortunately, I cannot tell the exact number, but we are speaking about multiple petabytes of data. Multiple teams use either private cloud or public cloud operated instances of Druid. Overall, about 1,000 hosts committed. And as I said, the first major contribution to this product started actually since Yahoo times. Druid actually pioneered the use of data sketches among the big data platforms. And this talk is going to be about, as I said, data ingestion, how we speed it up through a novel data structure that is called Oak, which has been developed in our team, which is actually a scalable off-heap concurrent key value map in Java. If this just sounds to you as a blob of words, don't be scared. We'll actually get down to the meaning of each and every word here. So please bear with me. So thanks, Itai, for actually making this part shorter for me. I'll just skim through it. But so just a short recap from Itai's talk. So in Druid, we basically have a pretty simple but powerful data model in which we have 3 types of creatures. We have timestamps. We have which is actually a primary dimension. We have other dimensions, and we have metrics. And these metrics can be either simple numeric functions or data sketches that we use for approximate aggregations of complex functions. On the internal side, the physical storage and serving are organized in a way that support most of the use cases in which we handle, in which data flows in and should be ingested on the fly. So most of the data is write once or append only. So take, for example, a use case like a mobile user analytics service that registers the events that happen across thousands of mobile apps. So all these apps report the what's going on inside there. So most of the events arrive in order in the order of their timestamps, time creation, and are rarely fixed. So the data is mostly write once and depend only, and the query is mostly focused on the time dimension first. So it only makes a lot of sense to use the data model, the schema that the Druid suggests. So the data is organized in a sequence of chunks that reflect an order of ingestion, and the chunks consist of segments. A segment is actually a logical unit, but you can think about a segment as a file that is ordered internally by time. So when a query is issued, the query routing subsystem within Druid actually figures out which segments should be hit in order to serve this query. So actually, Itai has a nicer picture of the Druid architecture, so I won't go into too much detail of that, but we have here a component that is named middle manager. Horrible name. You guys should do something about it. We all should do something about it. Okay. I like the previous name, real-time node, more. But there is some one other coming up that that is called indexer service that makes more sense to me. Okay, but so basically we are going to speak about the ingestion, so native ingestion in Druid. So as Itai said, there are processes that ingest the stream of events that that come from the outside and create those segments, throw them to deep storage, and once these and these segments can be accessed through the other type of nodes that are called historical nodes. So the whole point of Druid is that the data becomes immediately queryable. So it's once you ingest an event, it already contributes to the queries. So the queries hit both the middle manager nodes and the historical nodes. Middle managers used to consist of a hierarchy of processes that in which the lower level tasks are performed by processes that are called peons, and one ingestion task actually translates to one Java virtual machine. A more modern architecture is called indexer, in which that actually makes better use of machines' resources, and in this architecture, a task equals a thread. So each indexer task actually can do two things. The first one is as I said, to ingest the data, which might include updating some rollups, for example, doing some computation on the fly, and on the other hand, participating in the query serving process together with the historical nodes. So some performance caveats. So actually, the segment size is crucial for system performance. So it turns out that the queries are slow when the segments are either very big or very small, and the segment granularity is controlled by the indexer task settings. So there are actually two parameters here that control when to flush the segment to disk when it fills up. One of them is actually a hard limit of 5 million rows per segment, and the other one is a kind of recommendation of 300 to 700 megabytes per segment. So both are configurable. So once the first the smaller of them is crossed, the file is the segment is flushed from memory to disk, and it's actually not the and the data becomes immutable. So as I said, segments that are too small are not very good for query performance. So for that reason, Druid automatically merges the small segments in the background to create bigger files that can be that can be queried more efficiently. So a kind of thesis that we are trying to promote here, that with the memory becoming more with the memory becoming cheaper, we should have we should be capable of building actually bigger segments. So let's make some small math here. 5 million rows using sketches amounts to dozens of gigs of data. Okay, so this is apparently 1 or 2 orders of magnitude more than the current recommendation. So we actually are striving to build larger indexes in memory, so that the overall system will have to do less compaction work in the background going forward, and at the end of the day, serve queries faster and be more efficient overall. Okay, how many of you are still following me? Hope so. Okay, good. So the part that is crucial for the ingestion process is a component that is named incremental index. For the sake of the rest of the discussion, let me just call it I square. So this is a core data structure that is used by all indexing tasks. It's an ordered map of data rows that can accommodate point updates, point lookups, and range queries. As I said before, queries that are based on timestamps are very common. So we oftentimes run queries that between two timestamps. At the same time, it should be concurrent because modern machines, as you know, are multi-core CPUs. So queries and ingestion happen in parallel, and multiple things are going on concurrently. So, for example, locking the data structure for queries every time we make an update is not an option. So for that, we really need to use, and Druid does use actually a concurrent data structure that is actually allows synchronization at a very delicate level, and allows multiple reads and writes go in parallel. The incremental index, as similar to the system, comes in two forms: a plain index, which is just a collection of facts, or rollup that does a on-the-fly aggregation. It is built on the data structure that is taken from the Java standard library, the JDK concurrent skip list, that does exactly what was implements exactly the requirements described above, and it actually adapts the simple key value model of this data structure to the Druid data model, the data schema. So the keys are actually a concatenation of the timestamp with the other dimensions, and the values are a bunch of metrics. So now I'm going to ask a question for which no system architect has ever been fired, and this question is, how far does it scale? Okay, can we scale it? So remember that we are speaking here about the system that needs to scale this data structure to tens of gigabytes of data. Okay, so before I flip to the next slide, what would be your guess? What is the biggest impediment? What is the biggest bottleneck for scaling data structures in Java? Can you say it again? GC? Yeah, the garbage collection. GC is obviously the biggest impediment. So how many of you guys here are Java programmers? Hope so. Okay. So we all love writing programs in Java. It's having managed memory and garbage collection actually saves us a lot of headaches, and I shouldn't explain this stuff to you. The problem is that this thing has never been really designed for really big data applications. So it's fine when you run your program on a few with a few tens of thousands, hundreds of thousands of objects. But what happens when you come to the scale of millions? Well, GC costs. Okay, it steals CPU cycles, and more importantly, it needs a lot of RAM headroom. So our experiments on the I-square component show that with the I-square component show that 25% of ingestion time when in Druid, while ingesting stuff into I2 is actually spent on GC. Okay, so it really costs. And I can tell you even more, that in order to ingest a few gigabytes of data, you should into memory, you should actually pay up to twice as much RAM in order to have the garbage collection algorithms work in a way that don't slow the system too much. Once you go below, your slowdown would be much bigger than these 25%. Okay, up to the point when the system becomes non-responsive. So remember that. Well, you want to use Java? Fine, please pay up for memory. Okay, so here we come into play. Sorry, it took me too long to get to this point, but that's the story. So our goal is actually eliminate the GC overhead in I2 through better use of RAM resources and better scaling to the on the multi-core CPUs with the data size. So what we are actually looking for is the implementation that is GC insensitive, and the way we're going to do that is a low-level trick that that is not very common to Java programmers, which is take your data off heap. Okay, so all the Java objects are managed on a memory section that is called heap. This is where all the memory allocation and garbage collection algorithms run on. So the first caveat is that we take all the data off heap. Once we are off heap, it's once again the wild west of C++ programming, with very nice memory overflows, no bound checking, no automatic accounting of objects, etc., etc. So we want to build this order map for off-heap data storage with the same strong concurrency guarantees. Remember that this data structure is concurrent, and desirably, the overhead for managing all these data should be small. So here I use this occasion to promote our internal project that you could use regardless of being Druid developers. It's called Oak. It's actually started from an abbreviation of off-heap allocated keys, but we kind of drew our inspiration from the Druid religion. The Oak is actually a sacred tree for used to be a sacred tree for Druids. So without going into too much details of that, the Oak is a concurrent map with atomic semantics. It tries to bring you the best of the two worlds, the managed memory programming experience with the unmanaged memory performance. Our design principles are storing the keys and the values off heap. The metadata, which is actually the search tree on top of these keys and values, is stored off heap but remains small. We'll be shortly coming down to that. And since we want to use the memory efficiently, we actually have our own custom low overhead internal GC algorithm that is aware of the key value map semantics, and therefore is more lightweight. On the API side, you can use Oak exactly the same way you use the Java maps. It supports the standard JDK API. But if you want to be more efficient, you have to use an alternative API that's similar but a bit different, that is called Zero Copy for best performance. This API actually minimizes the number of copies between the off-heap and on-heap spaces, and also does the in-place updates like sketch up the updates of heap. Okay, so just a glance. It's not at the internal structure of Oak. It's not a data structure stock. We're not at the class here. Just to give you an idea about what's going on. So Oak has two parts. It has the bottom part is actually the off-heap storage in which we store our keys and values in big blocks of memory that we allocate and manage ourselves that are called arenas. The top part of this index is actually on heap, and it's actually very lean. It's a search tree in which the leaves are organized as big arrays that we call chunks. And these chunks, actually, for those of you who are familiar with B-tree technologies from the database systems domain, so the same ideology follows here. So the thing that we've built on the top part is actually a concurrent B-tree, and the bottom part is the off-heap storage. So there is one particular need in using chunks, which is we want to avoid as much as possible having a big number of metadata objects. So each of these chunks can actually host hundreds to thousands of key value pairs. So actually, the number of objects that the Java GC deals with is a few orders of magnitude smaller than the number of the key value pairs. So we don't actually have a metadata object pair and an off-heap key value pair, and this is actually our key for success. So I'm going to show you the results of a few experiments here, and believe me, there is of course all the algorithms that are used by Oak are theoretically sound. There is a paper and there is a proof, and there is all kind of nice stuff that the scientists like. But actually, at the end of the day, we have working code for it, and here are the results. Okay, so here is a result of building a key value map with 11 million key value pairs. Roughly, each key value pair is 1 kilobyte big, a little bit more. So as you see, the x-axis is the number of concurrent threads with which we build the stuff. So as you see, the standard on-heap implementation, the orange line maxes out at about 15 threads, and Oak keeps scaling quite nicely. The green line is actually a more naive implementation of off-heap storage, which actually takes just takes the objects off heap, but still keeps a metadata object or handle per each off heap object. So so there is still the same. It's still the same order of magnitude number of objects as the classic implementation. So its performance is somewhere in between. And so for gets, which are point reads, the graph actually shows the performance of the zero copy interface. Of course, when you start copying stuff from off heap to on heap, you pay some price, but it's still not too bad. Same here with the scans. We look at the performance of zero copy scans that can scan 10K 10,000 pairs each. We are good actually both in the forward scans and the backward scans. Actually, the specifically for the Java implementation, for the classical Java implementation, the backward scans are very inefficient, and we can do a much better job thanks to the fact that we have chunks. Now coming to the last part of it, how we use Oak for an I-square implementation. So this is a work in progress project, actually experimental, that in which we implemented I-square on top of OakMap. It's actually quite a bit of work because we need to both refactor Druid in order to accommodate this new kind of beast. Technically speaking, it's we implement it as a core part of Druid, but we are also open to build it as an extension to lower the friction at the first stage. As I said, we mapped the Druid schema to the OakMap concepts. We leverage the zero copy API for both for queries and for in place aggregation. Currently, we don't support sketches yet, but this will be our next step. We've just made the first contact with the community and opened a Git issue, and we expect this this whole project to be generally available sometime mid this year. So just a few of the experiments that we've run already at the system level, so that you believe me more. So we are in this experiment. We are trying to ingest 1 to 7 million rows into an index, and so we look at compare two implementations. One of them is based on Oak, and the other one is based on legacy. So as you see, Oak is pretty insensitive to how much memory it gets. It uses barely uses memory beyond its beyond what it means to store the bare bones keys and values, while the legacy implementation needs actually a lot of headroom in order to let the GC algorithms breathe. Otherwise, the performance goes down. So this is this experiment is the same, but we just work with the available memory without scaling the data. It's like a zoom in on ingesting 7 million tuples, and so this last plot is mainly probably the most interesting one. The memory occupied in comparison with versus the number of tuples ingested. So the raw data is the black line, and the blue line is Oak's memory is I-square memory consumption based on Oak. So you see that we barely add up any overhead to the bare bones data, whereas the legacy the legacy code uses a lot of more memory, and as I said before, GC requires twice as much. Okay, so you might ask why would I care? Well, people that run Druid at scale and use many machines at either in a private or public cloud and have to pay up for them, they know. So it really the question of economies of scale and scale matters. Okay, so at the end of the day, this implementation allows the system ops be much more memory efficient and actually run cheaper systems. Okay, so summing up, hopefully I didn't get you exhausted too much by this detour in the basic data structures class, but the takeaway from today's talk is that GC is critical for real-time ingestion performance in Druid, and actually it gets worse as we try to build bigger and bigger indexes. What we suggest here is an off-heap incremental index. It's an implementation based on our homegrown project named Oak, and we're really looking forward to collaborate with the community here and get this code actually into the production base of Druid sometime this year. Thank you so much. Questions?
When you are dealing with much larger how do you deal with longer or more late arriving data? So if you're creating a 10 gig width segment file, or that's your target, if you are indexing over an interval of 24 hours or something, has that come across, or is most of your data like arriving on?
Actually, it's a great question. For the time being, we mostly focus on the real-time nodes, but I think it's what we suggest here is like more of a solution than a problem, because as long as your data stays in memory in the real-time node, you can actually incorporate this late arriving data in the basic data structure without the need to dedupe it later when you merge between segments. Does it make sense?
Yeah. So you just keep a wider.
Yeah. Yeah, that's a. So we could take it offline, but basically, yeah, you could the longer the data stays in memory, the higher the chance you can incorporate the data that's coming up late, and the less the price, at least theoretically, that you pay for its reduction later on.
Is there any trade-offs with big data if you have smaller nodes or a smaller cluster, or does this really only benefit when you're working?
Yeah, great question too. Actually, we are dealing with this question as we speak here, because we are at the point when we just transitioned from component level benchmarking to system level benchmarking, and many things look different there. So when you do I/O, it actually can makes many things appear different. We are looking for a way to impact the settings in which the in-memory part is the bottleneck. Obviously, if the I/O is a bottleneck when you have a small scale system and your indexes are not really that gigantic, so maybe it doesn't matter so much what kind of data structure you use for the in-memory part. But if you want to be, I would say that if you want, as long as you want to remain more real time, more closer to the in-memory database performance, the closer you want to stay there, the more investment you do you should do in building bigger segments and serving them off memory. So it's just an off the top of my head answer, but this particular use case has enough applications in our internal products. Thank you.